Good morning and welcome. So we have been looking at the numerical discretization of conservation laws, and we have been focusing on the Burgers equation. The form that we try to get the conservation law discretization in is the conservation form, and that is to get the conservation property, also discrete. That is, when we sum up all the contributions, we would get the change in the whole domain governed by what is flowing in minus what is flowing out. So, and this conservation form is the following. So that is what we call 21. Our conserved variable jn plus 1 minus ujn divided by delta t plus, then we do the discretization of the fluxes such that we can write it in the following form, and we just take the explicit method, so then this is all at the time level n. So in that form we try to get it, and what we want to solve by that is equation, that is called conservation law. Conservation laws of the form that we saw when we have u dt plus usually a nonlinear flux function f of u with respect to x equal to 0. So that means these f that we have here, they should approximate the flux function that we have in our problem, and that should then be what we said consistent. And we have been focusing on the upwind method. So, and we have also been focusing on the Burgers equation. So for the upwind method for Burgers equation, and we have been here looking at the inversive Burgers equation. And that is when we have this f in the form, I think we call it 7, that is when we have f of u is equal to u squared half. And with that we can study basic phenomena like shocks and rarefaction waves, as we saw, and as you also have been now looking at in exercise 8. So, and then we have the different forms, and the form that is valid without if statement is the following. Verse 33, that we say the numerical flux function for the upwind method, discretize the inversive Burgers equation, is 1/2, and then we have here the uj squared half, so that we have the flux function f of u evaluated at uj. And then we have here the same, the uj plus 1 squared half minus, and then our characteristic speed turns out to be, in that case, the average of the uj and uj plus 1 half. We take that in absolute value. And then we have here the difference, uj plus 1 minus uj. And we have argued that is actually the same as if we would say that the flux function is given by this, if this is positive. 0, it's not, we can also take that. And it will be this part if the characteristic speed is negative. And for the exercise, we had clearly just one sign. We had only positive sign. So in that case, this will always be positive, and then we could choose just this as the flux. It was quite easy. But if we have a change of sign in u, it is advisable to use this form. And we shall also now do that when we continue the discussion. And the discussion now that we want to take is for the following situation. We want to have a problem, we want to see a problem where we have x, when we have u, and we have here the initial condition, so it is the u of x0, and we assume, just for as an example, that we have the ul is now ul, say it's -1, and the u right is +1. What do we expect here? We have studied that. What will we get when we want to solve that with the inviscid purpose equation?
Rarefaction wave?
Rarefaction wave, exactly. So we should expect that we get a rarefaction wave. That means after a while t, we should expect something like that. So that would be then the solution at u of xt. That is what we should expect. And the distance, if this is the origin that we assume here, then the distance traveled would be then here. That would be the distance would then be ur times t. That would be traveled then by this. So that is what we should expect, and this would be ul times t. Now let us see what the upwind method does. So, try that. So here we have the initial condition, exactly what we have there, -1 on the left and +1 on the right. So then we let it go. This is the exact solution, and the numerical solution stays at the initial condition. Nothing happens, which is completely wrong. Why is that? Well, let us see. We can look at this form because we can use that now. We will have at, when we are here close, or wherever we are close to here or close to here in the initial condition, we will have, say, the uj might be -1 and that might be +1. So we will have a 0 here. And then we will just get the uj square half, or this we will get here, which is 1/2 plus 1/2, which is 1, so we will get 1/2. And this will not change. So we will not get any movement in our solution. It will just stay where it is. So here the method gives us a wrong answer. Why does it that? Because it only assumes that we have shocks. And what we have here, if you think of it, when ul is smaller than ur, and we would have this as a solution, that would be an expansion shock. That would violate the entropy condition, the Lux entropy condition. But the method doesn't see it. So here we have a defect of the method. So we have to do something about that. The method recognizes that we have a rarefaction wave. So that has been observed, and there is a solution to this that is due to Harten. So we can conclude what we have seen here. We have applied with the explicit upwind method. Explicit upwind method. That is when we use this as the flux in the conservation form that we saw in the beginning. So the explicit upwind method yields a steady, and we know it is an expansion shock. So that is wrong. That violates entropy condition. It is not stable. So we have to do something. And the solution to that then is due to Harten. Let's see that. has been gotten the name Harten's entropy fix. So, let's try to understand what we should do. So in the critical situation, just at the discontinuity here, this becomes 0. So that's the problem. So you could also think of it that we have no numerical viscosity. Remember, if we divide this by delta x, multiply this by delta x, then this term here, with the 1/2 in front, you can regard that as a numerical viscosity, because this has then the same discretization as we would have for a viscous term. The Burger's equation, the new du dx, if we put that in this form, it would appear here in this form. So then we have here the numerical viscosity, which is 0 in the critical case. So we should give it some value so that we can overcome things. And Harten then argues the following. So then the uj plus 1/2, which we take it as the average of uj and uj plus 1/2. So that in the equation 33 is replaced by some quantity q of uj plus 1/2, where this is defined in the following way. So we keep this for to see what we try to do. So we try to, now we can take that again away here, delta x. We try to get this then some value different from 0 that is enough that the method recognizes that this is an expansion shock, and it should go away from that and get a rarefaction wave. And it's the following. We have the function q of u is equal to, we take the absolute value when things go fine. And then that is the case if the absolute value of u is larger than some threshold delta that we have to determine. But when it comes below the threshold, we want to take u squared plus this threshold delta squared divided by 2 delta if the absolute value of u is smaller or equal than delta. And then we can see even if u is 0, we get some value. If u is 0, we get delta squared over 2 delta, so we get delta half. So then we get something different from 0, so then we get some numerical viscosity here when we replace this by q of this. And what does this look like? Do a little graph. If we have now here the u, and we have here the q of u. So this modification of this average velocity. Originally, we have just the absolute value. The absolute value, we can do like this. So that would be just the absolute value. But this has the problem here at the origin, gets 0. So then we do something different. And what we do different is that we define a delta that we still have to do. Let's assume that we have it. We have a delta here, and we have the minus delta here. So then we will follow the same curve, the absolute value, up to the threshold. And from then on, we modify that to a quadratic function. So this is delta, this should be delta half roughly here. Let's see, it should be roughly something like that. So what we have here then, that is then the q of u. So this function, the reddish one. And this distance here, that is the distance what we identified as delta half. So then we get something there. So then it's just the question now, what should this delta be? And this delta, we can choose the following. So where continuous over there, where the parameter of the threshold delta can be determined by the following. That is 39. Delta is equal to the maximum of, we have uj plus 1 minus uj. That is the critical thing. And in the case that we looked at, this was 1 at the discontinuity, this was minus 1. So here we could get the 2 in our case. And then we limit that by the machine epsilon. So this is the MATLAB notation, and this is 2 times machine epsilon. And that is to avoid, so that is to avoid division by 0. So that it would be here. We don't want to have a 0 here. So then we will then, in the critical situation, in our case, then have this delta will be then, as we saw, 2. And then it will give us some numerical viscosity in the critical case. So then the numerical flux function for the upwind method that was originally this one is then changed to the following one. So then numerical flux function change to following 140, that we have the numerical flux function at the interface xj plus 1/2 is, and again we have the inverse Fergus equation that we discussed here. So everything is the same as we had originally, except for that this absolute value of the average is now replaced by this function q of this. So then we have then this, and that is then the q of uj plus uj plus 1/2, then times the difference uj plus 1 minus uj. So then form that we shall see will work. And again, we can now identify the numerical viscosity in the numerical flux function. So then, numerical viscosity in that was it in 33. We had identified that was the new numerical, that was the average, which is called the uj plus 1/2 delta x half. So we have then divided by delta x to see that we have here the discretization of the first derivative, as we would have when we discretize the viscous terms in the Burgers equation. Then this term together with the half, then that was the original one. So that becomes then, for the modified method, becomes for 40, new numerical is equal to, now we have instead of the cube of uj plus 1/2 delta x half. So that is the change. So we get here, we can discuss this in terms of numerical viscosity. And for the critical case that we discussed, so for UL is equal to -1 and UR equal to 1, then the new num that we saw here, that was 0 for 33 becomes, as we discussed, it was the delta is then the 2, and we get here in the critical case we get then the delta half, so it is then 1, so that becomes then the new num in our case becomes then actually delta x half for 40. So we get then something. And that turns out to be enough that the method recognizes that we have a rarefaction wave and that develops into a rarefaction wave. Let us see that. This was the example without entropy fix, where we had used the original form of the numerical flux function, 33. Now we want to use the one with the Harten entropy fix. So we have again the same initial condition, -1 on the left, +1 on the right. Then we let it go. And now we get something. It is not perfect, but when we do grid refinement, we will see it will converge. So now the method recognizes that we have a rarefaction wave and we get an approximation of that. So it works. So that is the thing that you should be aware of when you use the upwind method. When you get in this situation that you have, in our case, the UL smaller than u right for the implicit Burgers equation, that is a critical situation, and then one has to do something about it. When we go on, that is in the course, the follow-up course, computational heat and fluid flow, TP 4165, we'll look at similar problems on the Euler equations. We have a very similar problem there, and we do the same thing there, so we can also do this entropy fix then for the Euler equations. So then we know this, and now let us continue by some observation. What we have been doing, and also what you have been doing, is discretizing the implicit Burgers equation for different initial conditions. When you have a step, a shock moving, you had a cosine wave developing into a shock and a rarefaction wave. But what you observed was you did not get oscillations, if you think of it. You did not have oscillations. But when you remember what we looked for the linear advection equation, and we looked at a higher order method, the Lax-Wendorf method, we got oscillations. So there is now a concept to characterize that a method is not getting oscillations. And that concept is called total variation diminishing. That is an important concept for the discretization of conservation laws. And we can just by observation conclude that the upwind method is has the property that the total variation is not increasing. That is called total variation diminishing. Actually, we can prove it. We don't do it here, but we can do it. So we can conclude that the explicit upwind method if the stability condition is satisfied, that is for, we call it the Cmax, is then equal to, if we would have the general case for the conservation law, we would then have here the, let's see, if we take it for the implicit Burgers equation, that is good enough. And then for the general case, it would be then the average of the characteristic speeds with uj and uj plus 1. Here it is for the implicit Burgers equation. So that is then we should then take the maximum of this, maximum of all j, delta t. It is not the Cmax, sorry. It is because the Cmax is when we take that, it will be, in the end, it will be the same, but let us make a distinction. Because the Cmax is then just taking max j, uj directly. But if that is satisfied, then this is also satisfied. So if this is divided by delta x, if this is smaller or equal than 1. So we can say when the stability condition is satisfied, then this condition is also satisfied. So an explicit upwind, the explicit upwind method for this condition turns out that it has this property that I just mentioned, total variation diminishing. It should have been total variation non-increasing, but somehow it has become this name, total variation diminishing. And to be able to understand that, we have to define what it does it mean. So we look here at just one step. We look at the one-step method from n to n plus 1. The one-step method. And finite difference method for a conservation law. And we look at hyperbolic conservation law form 6, defined in complete domain all real numbers R, is called total variation diminishing. The acronym is TVD. So that is an acronym that we will find frequently in CFD. TVD, total variation diminishing. If the following holds, it is 41, if the total variation of the solution at the new time level is smaller or equal than the total variation at the old time level. So then we have to understand what is the total variation. So that will be then the next step, to look at the total variation to make this definition clear. So we continue the definition where the total variation of, say, un is defined by, call it 42, total total variation of the solution at the old time level n is equal to the sum. Now since it is defined, we said for the complete R, we can go from minus infinity to plus infinity, where we take the difference from ujn to the neighbor, j minus 1. So we look at the changes. And we look then the sum of the absolute value of all changes. Usually we do this for a periodic problem, then we just have to check it for one period. So what does that mean? Let's assume we have some initial condition. Let's see if we would have the shock situation. That would be then, say we have here our initial condition, u of x0. We would have something like that. We would have the origin. We would have here a couple of points. So we say we don't have anything, or we could have something also close at, doesn't matter. So these should, the stars should represent where we have our grid points. Then if we would apply our upwind method, say we would then have u of x, say it would just be a delta t, just one time step. So then what we will observe will be then that we will have, let's see, these ones will be unchanged. And this will probably get something down. This might get something up. And this will stay. So, but it will get, I'm exaggerating here a little bit, but the point is that the difference from one point to the other, if we sum that up, it is only this difference here. Here this difference is the same, because this distance and this distance and this distance together is the same as this. So here the total variation is staying the same. So the total variation that we have here, that would be then of u0. In that case it would be the same as the total variation that would be, say, of u1. And if we can then prove that, and we can actually do that for the upwind method, so then we would have, the method would be TVD. Total variation would not increase. If it's the same, that's okay. If you think for the cosine problem, we didn't let it go that far, but if you let go it further, then you will see the total variation would actually decrease. That is okay, but it should not increase. So that is the case that we have for our explicit upwind method. But if we have the following situation, we have again the same initial condition, u of x0. So again we have the same case. And then we would not apply the explicit upwind method, but we would apply, for example, the Lax-Wendorf method, or any other method that is not total variation diminishing. So then we might get the following. We might get something here, we might get something here. So then we would get something, do that. And you see here, the total variation would increase. Here we would have this change here would be above what we have had from the beginning. And also this undershoot here would add to the total variation. So here the total variation, say of u0, then would be smaller than the total variation of u1. And that is not TVD. So as soon as we start getting oscillations, we add to the total variation. And that is something that we don't want. It is not in accordance with what we expect from the solution. For the solution, the total variation should not increase. So the methods that have this property, that the total variation is non-increasing, we call it diminishing, these methods are called TVD, total variation diminishing. Okay, so then that will be now one criterion for the estimation, for the qualification of the methods that we shall discuss. Anyway, for the explicit upwind method, this property holds. So, then let's now look at some other methods. We have seen the upwind method does a good job, but when it comes to the case when we are in danger to get an expansion shock instead of a rarefaction wave, we have to do something. If we do this entropy fix, it is okay, otherwise not. Methods that are easier are, or one method that is probably the easiest method, and that is usually the one that you might try first. That is called the Lex release method. We have already seen it for the linear advection equation. The Lex release method. And now we want to apply it for conservation laws. That is then for conservation laws. Form 6. I write it here in this form equal to 0, and that is similar as we discussed it for the linear advection equation. It reads the following. The time discretization is now done by this trick. We do compute the solution at the new time level minus, and here we take the average of the neighbors at the old time level. So we take here then the uj plus 1n plus uj minus 1n half. So that is now our discretization of the time derivative. So this is the trick. Instead of having here ujn, the average of the neighbors is taken. And then the discretization of the flux derivative is done by a central difference. So we take here the flux function for our conservation law, this f here, u squared half for the Illicit-Burgers equation, at uj plus 1n minus f of uj minus 1n divided by 2 delta x. So that is 0. So you see here that we have a stencil that involves the neighbors at the old time level, but the old time level at j is not entering. So then the stencil looks like this. It's the same as we discussed for the linear advection equation. So we have here the j minus 1 and the j plus 1. And we have here, so this here is time level n, this is time level n plus 1. So here we have the j. So we have nothing here. So the stencil is like that. But this is the interesting thing. We have not the ujn here, only the neighbors. So, and for which j does this hold? If we do the numbering in the way from 0 to nj, Then we see we cannot apply it at 0, because we have no left neighbor minus 1. So we cannot apply it at n. So this would then be valid only from 1 to nj minus 1. And we have then to use the boundary conditions depending on the sign of the characteristic speed. So we have to use a boundary condition. U0 is equal to UA if for f prime of UA if that is greater than 0. So then we will have inflow. The f prime, that is the characteristic speed. It is u, simply u for the Invisib-Burgers equation. And we would use the boundary condition u nj equal to some ud if the characteristic speed at the right boundary is negative. Then something would enter from the right. If the characteristic speeds, in this case, left boundary are negative or positive at the right boundary, we could use, in any case, the upwind method at the boundary. So, then let's try to write this form of the Lax-Friedrichs method in a little bit different form. We want to write it in a form such that we can see whether it fulfills the conservation form or not. So we can then write the Lax-Friedrichs method can be written as following. First, it is very easy to see that when we just multiply by delta t and bring everything on the right hand side, that we get uj n plus 1 is equal to 1/2 uj plus 1 n plus uj minus 1 n minus delta t divided by 2 delta x times the flux difference of uj plus 1 n uj minus 1 n. So that is, and that would be the way you can code the method. But when we want to get it in the form of the conservation law, we want to have rather the ujn being here. And we want also then to see what are the fluxes. Here it is easy, we could add here an f of uj and subtract an f of uj to see that this is a flux or the difference of a flux average. So we can write this then in the form that we usually use, the following way: ujn plus 1 is ujn, so we add it, and then we have also to subtract it. We do it then in the following form. We take 1/2, now we take as uj plus 1n, so we subtract 1/2 uj here. So we have taken now this into account. Now we will take this into account. We have still to subtract another uj half. We do it then in the following form. We have then minus. We can also have here the 1/2 ujn minus uj minus 1n. So this is the same as this one here. We just added ujn and we subtracted it in this special form. So we have not done an error here. And then on the right hand side, we want now to write it in the form delta t over delta x, and then that we get some fluxes involved. So we then take the 1/2 in here, and we do what I said before. We add an added Ujn, and we subtract an added Ujn without doing any error. Then we get the following. We get then the f of Ujn plus f of Uj plus 1n. And we subtract something similar. F of Uj minus 1n and f of Ujn. So what we did, we added this and subtracted it here. So we did not do anything wrong. But now we can see the form that we get of the flux. The form of the flux is then already here, the same as we had what we discussed in the beginning today for the explicit upwind method, the average of the flux function. Evaluate it with the value at the old time level and the new time level. Sorry, the value at the j and j plus 1. Yeah, everything is at the old time level. And then we have here contributions that are also adding to the numerical flux. So we can write that in the following form. So from that we get that Ujn plus 1 is Ujn minus, now we take everything under the form of a flux, and we then get a flux function f of Ujn plus f of Uj plus 1n. Then we have taken this into account. And now we take this also into account. So then we see here, we have the 1/2, and that we can have here also. And if we factorize that into that, we have to multiply with the delta x over delta t. So then we do that. So then we get here the factorizing this delta x over delta t, such that this multiplication, this times this gets 1. And then we have here just to add Uj plus 1n minus Ujn. So that will be the flux at j plus 1/2 minus a similar thing. Let's see, we have this bracket here. That should close, let's see, that should close here. Exaggerating a little bit here. Now we get here the f of Uj minus 1n, f of Ujn, and here the same thing, delta x over delta t, and then we have this guy here. That is then Ujn minus Uj minus 1. So then, and then we have the whole thing. So this is then another form of writing the Lex-Riddichs method. And then you see that this here will correspond to the fj plus 1/2n, and what we have here, that will correspond to the fj minus 1/2. And then we have our numerical fluxes for the Lex-Riddichs method. Okay, I think we stop here and we write that down after the break.